Hello and welcome to this clip going through the electrode potentials level question. As always, every level question requires a plan, really, before you start, so you can think about what you're going to put. So to think about your plan, you have to look at the question and decide what it's asking you to do. So that means putting a diagram in including electron flow, putting an overall equation in, combining the two half equations that you're given, and using the electrode potentials to predict the direction of reaction, which will also help you decide which direction the electrons will flow in. So when you draw your half cells, you can actually use the electrode potentials to predict which of the half cells is going to be the positive and which of the half cells is going to be the negative part of the overall system. So the next part of the question says, over time after the battery has been turned on, the overall cell potential has decreased. It says to explain this in terms of the concentration of H+ ions in the hydrogen half cell. So to do this, you need to remember that each half cell is in equilibrium, and so will obey Le Chatelier's principle. So therefore, anything that affects or disrupts the standard conditions will cause a shift in the position of equilibrium. And because it's an electrochemical cell, that will start affecting the direction of electron flow. And if the electron flow moves in the opposite direction, then that will affect the Ecell value. So let's use these ideas. You don't have to write it down in such detail in your plan, but these are sort of things to think about as you do your plan. So you could maybe just scribble a few lines perhaps, just mentioning each of these. So the things that I've highlighted might be the things that you'd scribble down for a minute or so, thinking about what the question's asking you. So let's now go to the question itself and get started. So we have to do a diagram of each of the half cells. So we've got the basics in place: our platinum electrodes, our salt bridge, high resistance voltmeter, our solution of H+ ions, 1 mole per decimeter to the -3, and our two ions on the right hand side, both of them 1 mole per decimeter to the -3. So I'm using standard conditions as I go to construct my cell diagram. So I have to put down the conditions for the standard hydrogen electrode. So the hydrogen has to be a pressure of 1 atmosphere, and it needs to be set up at 298 Kelvin. Okay, now I have to go back to my electrode potentials and look at which one is more positive and which one is less positive. So obviously the hydrogen half equation at 0.00 volts is less positive, and the manganate half equation at plus 2.3 volts is more positive. So to work out the overall cell potential, you have to subtract the less positive from the more positive. So in this case it's quite easy because you're taking 0 away from plus 2.34. So your overall cell potential is plus 2.34 volts. Now in terms of the movement of electrons, so in an electrochemical cell, the electrons always move from the negative pole to the positive pole, or from the negative redox system to the positive redox system. So in this case, as we know that the manganate is more positive, that means that the manganate half cell is the more positive, and the standard hydrogen electrode is the more negative. So I've now labelled those up on my cell diagram. So I can now also say what direction the electrons move in, which I've now written out in green. So I think that covers me for drawing my label diagram and including the overall equation and an arrow to show the movement of electrons. Now I need to think about what's happening when the battery is turned on. So in this redox system, my hydrogen half cell is the more negative of the two, or less positive. So therefore it's reversed. So the direction that it actually moves in is from H2 to 2H+. So therefore what's happening is the concentration of hydrogen ions increases as this battery is left on. So what this does is it has an effect on the standard conditions, in that the concentration of hydrogen ions is now greater than 1.0 moles per decimeter to the -3. So the position of equilibrium shifts to the left in the reversed half equation at the bottom of the screen. As it does so, this actually uses up electrons. So if the electrons are used up, the standard hydrogen electrode will then become more positive. So if the hydrogen electrode becomes more positive, the difference between the two electrode potentials will go down. So if the hydrogen electrode's electrode potential becomes more positive, this makes the overall electrode potential, the overall cell potential, I should say, or Ecell, a lower value, so it decreases, like the question says. So I'm just going to have a quick check of everything I've done so far to make sure I've completed the question. So I have done the electron flow, I've done the half cells. I've not done an overall equation. I've done that. We've talked about this, and we've also considered all of that. So I now have to do an overall equation. So I'm going to put the overall equation up here. Now, to do this, I'm going to clear some space at the top. So how will I do that? I think by now you probably realise what the question is about. So let's now think about the two half cells. So what we've got to do is to look at the half equations. In particular, what I'm going to focus on are the electrons. So you can clearly see that the number of electrons is not balanced. So what I've got to do is multiply each of the half equations up so that they have a lowest common multiple. So I've got to multiply the top one by 5 and the bottom one by 2, so I have 10 electrons both sides. So now I have my two half equations multiplied up so that I have 10 electrons, and I can cancel the electrons out. And what I've also got to do is cancel out the hydrogens. So you can see that there's 10 hydrogen plus, 10 H plus on one side and 16 H pluses on the other. So that's my overall cell equation at the top. Now you may be thinking, hang on a second, why are there 5 H2s on the left hand side of my cell equation, where in the half equation the 5 H2 is on the right hand side? Remember a little bit earlier, down at the bottom of the screen we were able to deduce that because of the different more positive and less positive electrode potentials, one of the half equations is reversed. So the top half equation is reversed in the two at the top right hand corner of the screen. So essentially that is read from right to left, and the manganate half equation remains as a reduction, so that actually is read from left to right. Okay, I think that pretty much wraps it up. There were some tricky bits in there, but provided you stick with the logic and apply your Le Chatelier's principle and make sure you've answered every single part of the question, it should be fairly doable. Okay, thanks for listening. Thanks for your patience on this slightly longer clip on one of these types of questions. And until next time, thanks a lot and see you soon.